engineers are carving through the heart of England, building a future connection. This is High Speed 2, a project of unprecedented engineering scale. How do we maintain such precise alignment across hundreds of miles of terrain? To answer that, we must return to the Victorian roots of British rail. For decades, the existing arteries of British transport have reached their breaking point. Bottlenecks and outdated infrastructure are stalling economic connectivity between major industrial hubs. Euston Station, the gateway to the north, requires a transformation for the next century. The challenge is carving a new path through a landscape defined by history and ecology. Planners chose a design to minimize the environmental impact while maximizing speed and capacity.
It requires balancing massive structural loads with the delicate needs of local ecosystems.
The journey of 1,000 miles begins with a single, highly contested survey. Before the first shovel hits the earth, fabrication centers must produce the components. Automated precision ensures that every structural element meets rigorous safety standards. These rings will eventually form the skeleton of the tunnels beneath the Chiltern Hills. Access is the hidden struggle of infrastructure, creating routes just to build the route. The TBMs are marvels of engineering, assembled underground in deep, restricted spaces. They exert thousands of tons of force to push through compacted chalk and clay. The moment of ignition marks the beginning of the most complex tunneling project in Britain. Slowly, the machine bites into the earth, beginning its journey beneath the hills. Spoil removal is a logistics nightmare, requiring continuous belt systems to clear the waste. The extracted chalk is reused to reshape the land, turning excavation into restoration. Human oversight remains critical, even in the most automated environments on the planet. Sensors monitor every subtle shift in geological pressure, preventing surface instability. As the machine advances, it places concrete segments to secure the tunnel structure instantly. Above ground, the focus shifts to massive viaducts that will carry tracks over valleys. Each pillar is a gravity-defying tower, designed to withstand the immense load of high-speed rail.
This is the spine of the railway, taking shape across miles of varied terrain.
Giant launching gantries lift these segments, placing them with millimeter precision. It is a mechanical dance, performed thousands of times under strict quality control. With each span, the path towards London grows more solid and defined. Engineering is not just math. It is human perseverance against the physical world. Before the first shovel hits the earth, fabrication centers must produce the components. Even the ballast and sleepers are engineered to dampen vibrations and ensure smooth transit. Every millimeter of track must be perfectly leveled to allow trains to travel safely. Precision is the only language that matters when speeds exceed 200 miles per hour. The landscape is being rewritten, one section of rail at a time. Beneath the surface, engineers must navigate a tangled web of existing city infrastructure. One wrong move could disrupt critical services for millions in the city above. Working in these confined spaces requires immense skill and specialized safety protocols. But even the best plans hit unexpected obstacles hidden deep within the earth.
The team must adapt, solving technical puzzles that were never in the original blueprint.
Replacement of these massive parts is done in the dark, under intense pressure. Restart sequence initiated. The heavy industrial boring machine powers up, beginning its relentless advance through the Earth's crust. Managing water influx is a constant battle, preventing saturation from compromising structural integrity.
Slurry walls create an impenetrable barrier, protecting the excavation from groundwater.
At night, the site glows like a futuristic city, working around the clock. Safety is not a feature. It is the fundamental requirement for such extreme engineering.
We also ensure the project respects the communities living right at the surface.
The breakthrough is a quiet victory after months of relentless, high-pressure excavation.
Breaking through to daylight is the highlight for every tunnel engineer involved.
This machine has done its job, carving a path through the impossible. But the tunnel is only a fragment of the gargantuan puzzle pieces.
Tracks now snake through miles of terrain, connecting distant sections into a whole. Systems alignment is checked with satellite-guided precision to ensure safety. This system will allow high-speed trains to pull power directly from the grid.
Signaling control systems are the nervous system of the entire network.
It begins to look like a railway, an entity that will change travel forever.
It is the culmination of years of labor and scientific ingenuity.
Returning to the start, the massive effort is finally visible in its scale. We solved the geological mysteries and connected the landscape with permanence. The machine that seemed so impossible is now just one part of the story. It provided the bridge between two worlds, the subterranean and the open air.
Looking into the dark, we remember the challenge we set out to solve.
The solution was found not just in machines, but in the collective human intelligence.
The mission was accomplished through persistent, innovative engineering.
HS2 is now a defining feature of the country, stretching hundreds of kilometers.
It is a testament to the scale that modern construction can achieve.
Every meter of concrete and rail represents 1,000 decisions.
Breaking through to daylight is the highlight for every tunnel engineer involved.
When operational, the project will transform the nation's economic landscape. The impact is already being felt, signaling a new era for infrastructure. But even as this project matures, the next engineering challenges are being plotted.
And somewhere else in the world, engineers are already attempting something just as extraordinary.